Hello students, in the previous class we have completed the packing efficiency. We have seen the formula and three important derivation for your syllabus and even for your annual examination. There is 3 marks question that we have seen. One is packing efficiency of simple cube, second one is packing efficiency in case of HCP, CCP, or you can call it as face centered cube, and even in case of body centered cube also we have seen. The next part of the syllabus is calculation of a density in solids, right? So there is one important formula. With that formula we have to further solve 3 marks question, right? So one problematic question will be from first chapter, that is on the calculation of density in solids. Okay, in the today's class we'll go with the calculation of density in solids. So the first concept is calculation of density in solids, right? So there is one important formula for the calculation of density, and in previous classes, which means in PUC as well as in lower classes in 10th, so you have studied that density is always is equal to mass by volume, right? So density means mass by volume, right? So that we can call it as in terms of solid, that is a mass of unit cell, right? So whatever the unit cell you take, it may be BCC, FCC or simple cube, divided by volume of the unit cell. What is its volume? So that if we divide, we will get the overall density of the unit cell. That is nothing but mass of the unit cell divided by volume of the unit cell. Therefore here, since the cube consists of, which means the simple cube, and similarly BCC and FCC, body centered cube, face centered cube, consist of some atoms, right? So therefore here we have to include the total number of atoms also, right? So due to inclusion of the total number of atoms, so this density formula is just modified into Z into M divided by A cube into Na, right? So it is termed in terms of ZD is equal to Z into M divided by A cube into Na, right? So where D represents, right? What is the D represents? So that is density, right? So Z represents number of atoms, right? So M represents mass of the substance, right? And A represents, that is the edge length, and Na represents the Avogadro value, that is a constant value, 6.022 10 raised to 23 per mole, right? So here I will write this one. So wherever there is a D, so it is known as a density, and Z means number of atoms, right? So how many number of atoms present in a simple cube? Only one. In case of FCC there are 4 atoms, and in case of BCC there is 2 atoms, right? And M is mass. M is generally recognized as a mass, and A is the edge length of the cube, right? So that is the edge length of the cube, and Na represents the Avogadro value, right? So Avogadro value, and that is a constant value. We know that one, Avogadro value 6.022 into 10 raised to 23 per mole, which means with the help of this formula we can calculate the density. If they ask density, we can calculate density. If they ask mass, so then we can calculate by putting the value of density, right? So out of these 5 values, they will give 4 value, and you have to calculate out of this 4 value, you have to calculate 1 value, right? So further we'll see how to calculate the density in case of given problems, right? So in the last class we'll see that one, right? So and the next concept is just remember this formula, that is D is equal to Z into M divided by A cube into Na, where Z represents the number of atoms, M represents the mass, D represents the density, and A represents the edge length, and Na represents the Avogadro value, and the constant value, that is Avogadro value, is 6.022 into 10 raised to 23 per mole. And the next important concept here after studying density, that is imperfection in solids, right? So it is defined as imperfections in solids, right? So solids are generally having some kind of disturbances. Disturbance means irregularities in the arrangement, right? So if you take any crystal system, if there is a missing of atoms, if it is not completely made up of all the same kind of atoms, then it is generally recognized as a imperfections in solids, right? So imperfections is also known as irregularities, right? So the irregularities in the arrangement of atoms, right? So whenever the atoms are arranged, so if there is any kind of irregularities in the arrangement of atoms, so E is called imperfection, or it is also known as defect, right? So you can call it as imperfection also, or sometimes you can also call it as defect also, right? So that is nothing but irregularities, right? So there is no any regular pattern or regular arrangement of atoms, that is generally recognized as imperfections, or which is also known as defects, right? So both words are same. Irregularity is also same, imperfection is also same, and defect is also same, right? So generally there are two types of defect, right? So defects are generally classified into two types. So one is generally called as a point defect, right? So another one is generally called as a line defect, right? So first one we will call it as a point defect, and second one is generally called as line defect, right? So in point defect, what happens whenever there is a irregularities, right, or the deviation from the ideal arrangement around a particular point or an atom, right? So that is generally called as, right? So that is generally called as point defect, right? So here I will write point defect means, right? So the defect which causes, right? So the defect which causes around a particular point, around a particular point, or so it is also recognized as the deviation from ideal arrangement, deviation from ideal arrangement, or so deviation from ideal arrangement, right? So that is generally called as point defect. And in case of line defect, what happens? The irregularities or deviations from the ideal arrangement to the entire row or entire column, right? So defect which causes in entire row, right, of lattice points, right? So in case of the particular arrangement of lattice points, if there is a complete missing of one line, or it may be in terms of row, or it may be in terms of column, that is generally recognized as the line defect, right? So I will show here the representation. So for example, if I take this normal side, that is normal representation, right? So in both the cases we'll take here, and there will be a particular arrangement of atoms here, right? So this is an arrangement of atoms. Similarly here also there is a particular arrangement of atoms. So here if you observe, again it is the same, right? So this is before defect, right? So these both are before defect, right? So there is a regular periodic arrangement of atoms. So this is in the normal condition. So when it converts or after defect, right? In case of after defect, so in case of point defect, what happens? So there will be a missing of atom or a substance from a particular point. There is a missing of atoms or substance from a particular point. For example, here if I draw, the arrangement may be like this. Right? So here if you observe, there is a missing, right? So here there is a missing, here is also missing, which means at a particular point. So this is a specific position where there is a missing of ion taking place, right? So here there is a missing of ion, right? So this missing is at a particular point. I can say that. So the missing of a lattice point or the missing of atom at the second column and second atom, that is at the second column and second atom, right? So that second atom is missing, therefore it is generally called as point defect. So but in case of line defect, what happens? So if you see the diagram here, so here in this case there is an missing of complete row or there's a missing of complete column, right? So here if you observe, so it might be like this, right? So the arrangement might be like this. So here there is a complete missing of, here if you observe, there is a complete missing of the second column, right? So this is completely called as line defect. So this is known as line defect, right? So are you getting the difference between point defect and line defect, right? So in case of point defect, what happens? The defect which causes around a particular point, right? So at exact position we can say that there is particular point or deviation from the ideal arrangement, right? So which means generally it was ideal, right? And before defect and after defect, what happens? There is a missing of one or two ions at a specific point or at a specific position that is generally recognized as point defect. But in case of line defect, what happens? So defect which causes at the entire row or it may be entire column, right? So row or it might be column, that is entire, this word is very, right? So entire row or entire column is generally recognized as lattice points. And if you see, this is before defect and after defect, what happened here, right? So line defect, the complete missing of the second column, or there may be complete missing of first row, second row, like this, right? So that defect is generally called as line defect. Therefore, imperfection in solid is nothing but irregularities in the arrangement of atoms is generally called as imperfections in the solids. There are two types of imperfections. One is point defect and second one is line defect. Okay, further if you observe here, the imperfections in solids, right? So those are generally recognized as the irregularities in the arrangement of atoms is generally called as defects, or it may be called as imperfections in solids. So the types of effects or the type of defects are generally in terms of imperfections. There are two main classifications that we have seen. One is a point defect, another one is line defect that we have already seen. So one is particularly the point defect, another one is generally recognized as the line defect, right? So further this point defect and line defects are subclassified, right? So these are further subclassified, but for your syllabus the complete study is about point defect. There is no study about, there is no any kind of information in case of line defect. So they have given the particular study about the point defect, right? So in this point defect, right? So further it is divided into three types of point defect. One is stoichiometric defect, second one is impurity defect, and third one is a non-stoichiometric defect, right? So first one is stoichiometric defect, second one is impurity defect, and third one is non-stoichiometric defect, right? So in stoichiometric defect, it is further divided into four types: vacancy defect, interstitial defect, Fresnel defect, and Scorsky defect, right? So the first kind of point defect is further subclassified into three types. One is stoichiometric defect, second one is impurity defect, third one is non-stoichiometric defect, right? So in stoichiometric defect, it is further classified into four types. One is vacancy defect, second one is interstitial defect, third one is Fresnel defect, and fourth one is Scorsky defect. And second main in case of point defect, that is impurity defect, right? So there is no further subclassification. It is only one type, that is impurity defect. And in case of point defect, the third type is non-stoichiometric defect, right? So in case of non-stoichiometric defect, it is further classified into two types. One is metal excess defect and the next one is metal deficiency defect, right? So now we will define what is vacancy defect, interstitial defect, Fresnel defect, and Scorsky. These are very simple. If you understand the one concept, the same thing is applied to the all the kinds of defect which you see in case of point defects. Okay, as we said that the first important defect in case of point defect, that is generally called as stoichiometric defect, right? So I will write here. So it is generally recognized as stoichiometric defect. Right? So in case of stoichiometric defect, right? So the defect in which there is generally change in the thermodynamic values like volume, or there may be change in the pressure, or there may be change in the, right? So temperature, that brings about the overall defect in the solids, right? So generally it is also known as a thermodynamic defect. It is generally recognized as thermodynamic defect, right? So which means the defect caused due to the thermodynamic changes, generally volume, temperature, or pressure, if there is a change in temperature or pressure or volume, so there will be a movement of atoms. That movement of atoms, or it may be missing of atoms, that generally brings out the overall defect in the molecule or overall defect in that substance. That is generally called as a stoichiometric defect. Right? So, and as we know that, so there are two types of stoichiometric defect. One is intrinsic defect, and it is also known as interstitial defect. Right? So intrinsic means within the molecule. These all defects which are in stoichiometry are generally taken in terms of intrinsic. Intrinsic means within the substance or within the compound or within the molecule. These are generally called as intrinsic defects. Right? So which means within the molecule. Right? So therefore one more word we can add here, that is known as intrinsic defect. Right? So intrinsic means within. Right? So the defects which takes place within the molecules are generally recognized as intrinsic defect. Right? Stoichiometric is also same. Intrinsic is right, so within the molecule, and stoichiometric are also called as thermodynamic, because whenever there is a change in pressure, whenever there is a change in temperature, or whenever there is a change in the volume, these defects takes place in case of molecules or the compounds. Therefore these are generally recognized as stoichiometric defect. So in that, first important defect is called as vacancy defect. Right? So the first important defect is vacancy defect. Right? So according to this defect, right? So whenever some of the lattice sites are vacant, the crystal, and they are said to have the vacancy defect. Right? So which means there is a missing of some kind of atoms. Due to that missing, there will be an creation of vacancy. There will be an creation of vacancy. So therefore that kind of vacancies are generally called as vacancy defect. Right? So I will explain with the representation here. So if you take a square, right, so which is made up of atoms, molecules or ions, right? So this is completely before defect, right? So this is a normal side, right? So this is a before defect. Right, so this is completely before defect, and when it converts into the defect, right, so then what happens, there is a missing of one or two atoms. Right? So here if you see, here if you observe, there is a missing of atoms here. Right? So these atoms are missed from the normal position, and this is generally called as a vacancy defect. This is generally called as vacancy defect, and this diagram is after defect, which means the defect which causes due to the missing of atoms, right? So the defect which causes due to the missing of atoms from its normal site is generally called as, right? So, or you can call it as complete missing of atoms, which means they are going away, or going out from the ideal arrangement or a regular arrangement. That is generally called as missing of atoms. Completely missing of atoms is generally called as vacancy defect. That is the first type of defect. And the second type of defect is generally called as interstitial defect. It is known as interstitial defect. Right? So in this case what happens, there is a movement of these atoms from normal position to interstitial position. Interstitial means in between there is an elements, or in between there is an atoms, there is an space. Here if you observe, so in between these four elements or these four atoms or molecules, so there is an space. This empty space is generally called as interstitial space, right? Which means the atom will not completely miss from the crystal system. It will be within the crystal system, but it will move from its own direction to the interstitial position. That is generally recognized as interstitial defect. So here I will show how it will become. So in case of representation, okay, if you take this arrangement of atoms in case of crystal system. So this is a normal, we can call it as a before defect, and after defect what happens? So there will be a movement from its ideal position right. So this atom or a element or substance which is present here, it comes here, right? So initially its position was here, right? So its position was here, but it has changed its position from here to here. And similarly here also one atom was there, so it has changed its position from here to here, right? So initially its position was here, which means there is a movement of atoms from its normal side to interstitial side. Here if you observe, so there is a movement, right? So there is an movement, right? So this movement is generally called as interstitial defect. Initially its position was at the first row, second atom was there, so it has come in between these four atoms, right? So it has come in between these four atoms. That is generally called as interstitial defect. So therefore before defect it was normal, and after defect it is generally called as interstitial defect, generally called as interstitial defect, and it is generally called as after defect, right? So there is a greater difference between the interstitial defect as well as vacancy defect. Vacancy means complete missing, which means if you count here, so the number of atoms before defect are not equal to the number of atoms after defect. But in case of interstitial, what happens? If we count here, there are 9 atoms. Here also there are 9 atoms, but there is just a change in the position. That is generally called as interstitial defect. And next, third important is, that is called as Fresnel defect. So that is the third type. And fourth type, that is called as the Scorsky defect. That is just the name of scientist, Fresnel as well as Scorsky. Therefore these are termed as Fresnel defect as well as Scorsky defect. So in case of Fresnel defect, what happens? Dislocation of cations from the normal side to the interstitial side, right? So the same vacancy defect, right? It is same, exactly similar to the interstitial defect, in which what happens? So there is a dislocation of cations from its normal side to the interstitial side, right? So you can define, so dislocation of cations. Remember, here just we are talking about cations, not anions, only cations from its normal side to interstitial side, right? And it is a type of interstitial defect, right? It is generally called as, it is a type of interstitial defect, right? So which means Fresnel defect is nothing but the interstitial defect in which the most important thing is only cations will move from its normal position to the interstitial position, which means there is an cation which is present here, it can move from its original position to the interstitial position. That is generally called as Fresnel defect. And in case of Scorsky defect, it is defined as both missing of cations and anions from crystal lattice, right? So missing of both cations and anions from the crystal lattice. So if you take any kind of crystal, if there is a missing of equal number of cations and anions, that is generally recognized as a Scorsky defect, right? So here I can draw this one, how the Scorsky defect takes place. So if there is a particular arrangement of atoms, so these are, consider these as a proton, that is plus charge, and these are negatively charged. All these are negatively charged. So here I can show that this is negatively charged. And after the defect, what happens? There is a missing of equal number of cations and anions, right? So if one cation is missing, along with that one anion is also missing. So therefore I can draw here, right? So like this. So if you observe here, there is a missing of one cation and missing of one anion, right? So here there is a missing of this cation and this anion, right? So therefore, whenever there is a missing of equal number of cations and equal number of anions, that defect is generally called as Scorsky defect. But remember the definition, that is both missing of cations and anions from the crystal lattice, that is generally called as Scorsky defect, right? So this is also similar to the vacancy defect. Vacancy means there is a complete missing. There is a complete missing. But in case of Fresnel defect, what happens? There is just a delocalization of cation. Delocalization means it is generally called as interstitial defect. Therefore, Fresnel defect is similar to the interstitial defect and Scorsky defect is similar to the vacancy defect, right? So these are the four important classifications of stoichiometric defect. First one is vacancy defect, second one is interstitial defect, third one is Fresnel defect, and fourth one is Scorsky defect, right? So in the next class, we'll see what are the main differences between the Fresnel defect and Scorsky defect, right? So what we have learned today, the first one is calculation of density in solids. So that is D is equal to M divided by V, which means D is equal to Z into M divided by A cube into Na. Further, we'll solve problems on these formulas. And further, we have seen the imperfection in solid, that is irregularities in the arrangement of atoms, is generally called as imperfection or defect. The main kind of defects are two types. One is point defect, another one is line defect. And this point defect and line defects are further classified into three major types. One is stoichiometric, and second one is very important thing, that is impurity defect, and third one is non-stoichiometric defect, right? And in case of stoichiometric defect, we have seen the four types. One is vacancy defect, second one is interstitial defect, and third one is Fresnel defect, and fourth one is called as Scorsky defect. Okay? So this is all about this class, and we'll continue in the next class with the differences between the Scorsky defect and other type of defect, that is the impurity defect as well as non-stoichiometric defect. Thank you.